Listen to me carefully. The reality you experience every single day, the solid ground beneath your feet, the familiar tick of the clock on your wall, is a fragile illusion. For decades, we thought we had the grand architecture of the cosmos figured out. We built towering equations, mapped the grand tapestry of space and time, and convinced ourselves we understood the birth, the life, and the inevitable future of everything that exists. But then, a colossal eye peering deep into the dark infrared corners of the universe sent back a collection of images that fundamentally shattered our confidence. What the James Webb Space Telescope has laid bare before us is not just a collection of distant glittering points of light. It is an impossible anomaly. We are staring back in time at colossal, fully formed galaxies shimmering in an epoch of the universe when, according to all our established laws of physics and cosmology, there simply should not have been enough time, matter, or energy for them to exist. It is as if you walked out onto your front porch tomorrow morning and discovered a fully grown ancient oak tree where a seed had been dropped only seconds before. Something is profoundly wrong with our timeline and the very foundation of how we understand the evolution of the cosmos is hanging by a thread. Before we dive deep into the heart of this cosmic mystery together, take a quick moment to hit that subscribe button and ring the notification bell. You are going to want to stay with me through every single step of this journey because the truth we are about to uncover changes everything. To understand why the physics community is genuinely reeling right now, we have to look back at the elegant, carefully constructed masterpiece we thought we had finished painting. For the better part of a century, cosmologists like myself built a story of the universe that felt almost complete. We called our reigning theory the standard cosmological model, very often referred to in the halls of physics as the lambda cold dark matter paradigm. It was our ultimate blueprint, a sweeping historical narrative explaining how a hot, dense, nearly uniform sea of subatomic particles transformed into the vast cosmic cathedral of stars, planets, and galaxies we see all around us today. Think of it like building a grand cathedral or growing a historic, ancient city. You do not wake up one morning to find towering stone spires, stained glass windows, and paved boulevards springing up overnight from empty soil. It takes generations of layered construction. First, workers clear the bedrock. Then, single stones are quarried and dragged into place, laying the foundation block by block. Only after decades or centuries do the grand arches rise and the soaring towers touch the sky. For decades, we believed the universe was built on this exact same principle of patient hierarchical assembly. In the beginning, roughly 13.8 billion years ago, the universe exploded into being. In those opening moments, matter was smoothed out with astonishing uniformity, like the surface of a perfectly still pond. But there were tiny microscopic ripples in that primordial soup, imperceptible fluctuations, where matter was just a fraction of a percent denser than average. Over hundreds of thousands of years, the relentless pull of gravity went to work on those faint imperfections. Gravity is a cosmic hoarder. It pulls matter toward matter, gradually gathering invisible scaffolding made of cold, dark matter. It took hundreds of millions of years for the first pockets of hydrogen and helium gas to collapse under their own weight to ignite the very first lonely stars. From there, our established physics said that galaxies had to grow the hard way through a long, messy process of cosmic mergers. Small clusters of stars would collide and fuse to make dwarf galaxies. Those dwarf galaxies would slowly drift through the dark, pulled together by gravitational tides across billions of years, gradually clumping into intermediate spirals and grand ellipticals. 3. In our standard timeline, creating a massive, sprawling, star-rich galaxy was supposed to be a slow generational marathon that took billions of years. To test this narrative, we rely on the most magical feature of our cosmos, the finite speed of light. Light travels through the vacuum of space at roughly 186,000 miles per second. That means whenever you step outside at night and look up at the stars, you are not looking at the universe as it is right now. You are looking at an album of ancient photographs. The light from the sun takes over 8 minutes to reach your eyes. The light from Andromeda takes over 2 million years. And if you look far enough into the deep expanse of space, you are looking directly into the deep past. For years, our finest optical instruments, like the beloved Hubble Space Telescope, gave us breathtaking views of the cosmic midlife. Hubble showed us galaxies colliding, stars being born, and nebulas glowing with celestial fire. But Hubble hit an impenetrable wall. Because the universe is expanding, light emitted by the earliest stars has been stretched, pulled across billions of light years like a piece of elastic, shifting its wavelength out of the visible spectrum and down into the invisible warmth of the infrared. To peel back the dark ages of the cosmos and witness the very birth of the first structures, we needed an instrument of unfathomable sensitivity. We needed a telescope that could detect the faintest whisper of infrared heat from the edge of time itself. That was the James Webb Space Telescope. We expected it to show us the delicate, ragged, primitive beginnings of the first baby galaxies. But what it actually showed us turned our neat, orderly cathedral entirely upside down. When we finally unfolded the golden hexagonal mirrors of the James Webb Space Telescope 1 million miles from Earth, we thought we knew exactly what we were going to find. We pointed its incredibly sensitive infrared cameras into a seemingly empty, dark patch of the sky. We were looking for the dawn of time. We were expecting to find the cosmic infants, the very first, very fragile, chaotic clusters of stars pulling themselves together out of the dark ages. According to every simulation, every equation, every textbook we have ever written, those early galaxies should have been small, messy, and dim. But when the data streamed back to our screens, we sat in stunned silence. The mystery did not just deepen. It entirely upended our understanding of cosmic evolution. Instead of faint, ragged baby galaxies, we saw monsters. We stared back at a time roughly 300 million years after the Big Bang, a mere blink of an eye in cosmic time. To give you a sense of scale, if the entire 13.8 billion year history of the universe was compressed into a single human lifespan of 80 years, we were looking at a toddler just a year and a half old. At that age, you expect a baby to be barely walking. Instead, we found a fully grown, heavyweight bodybuilder lifting weights in the cosmic nursery. One of these objects, a glowing red entity we cataloged from our deep surveys, is so unfathomably bright and massive that it defies all logical explanation. We calculated its redshift, the scientific yardstick we used to measure how much its light has been stretched by the expansion of space. The redshift was over 14. That number confirmed we were looking at a time when the universe was less than 3% of its current age. And yet, this single galaxy stretches across thousands of light years and shines with the light of hundreds of millions of suns. Let me break down exactly why this breaks our brains. To build a massive, luminous galaxy like that, you need two things: time and raw materials. In the standard model of the universe, gravity is a painfully slow worker. It has to pull together cold, dark matter into a vast, invisible halo, which then acts as a gravitational sink to drag in primordial hydrogen gas. That gas has to cool, collapse, and ignite into stars. Then those first stars have to live out their lives, explode, and send shock waves out to trigger more star formation. It is a slow, methodical, generational process. But the objects we are seeing with Webb are pouring out light from mature, heavy stars. We are even detecting the chemical signatures of heavy elements, like oxygen, woven into their light. Think about what that means. Oxygen is not made in the Big Bang. The Big Bang only made hydrogen, helium, and a tiny dusting of lithium. Every single atom of oxygen in the universe was forged in the nuclear furnace at the core of a massive star, and it only gets released into space when that star violently explodes in a supernova. For us to see heavy elements in a galaxy that existed just 300 million years after the beginning of time implies an impossible paradox. It means entire generations of massive stars had to be born, live out their entire life cycles, explode, and seed the surrounding gas with heavy elements, all in a fraction of the time we thought was physically necessary. It is as if you walked into a bakery that just opened 5 minutes ago, and the baker hands you a complex, beautifully decorated, multi-tiered wedding cake that takes 10 hours to bake. The timeline simply does not add up. The physics we rely on to explain the growth of structure in the universe is loudly colliding with the undeniable reality of these images. We are forced to ask a terrifying question. Did the universe age much faster in the beginning than it does now? Or is our entire understanding of how matter comes together fundamentally, spectacularly wrong? The mystery is no longer a tiny anomaly in the data. It is a blazing red alarm bell ringing across the cosmos, telling us that the deep past is hiding a secret we are only just beginning to comprehend. When you push the data from the James Webb Space Telescope to its logical conclusion, you run headfirst into a profound, suffocating contradiction. In physics, when your observations refuse to match your equations, you have encountered a paradox. And the paradox we are confronting today strikes at the very heart of how we believe energy, matter, and gravity behave. Let me lay out the two horns of this dilemma for you, because once you see them clearly, the impossibility of our current situation becomes undeniable. The first horn of the dilemma is what my colleagues and I call the cosmic budget problem. In the infant universe, we know with incredible precision how much regular matter existed. We know this because of the cosmic microwave background, the pristine thermal echo left behind shortly after the Big Bang. That radiation tells us that the early universe had a strictly limited budget of normal baryonic matter, the protons, neutrons, and electrons that make up gas, dust, and stars. Now, when a cloud of gas begins to collapse under its own gravity to form a star, something remarkable happens. As the star ignites, its intense light and solar winds push outward against the remaining surrounding gas. It acts like a built-in thermostat. In the modern universe, this process is notoriously inefficient. Galaxies typically convert only 5 to 10% of their available gas into stars. The rest is blown away, heated up, or kept suspended in a diffuse state. Yet, when we calculate the mass of the stars inside these early monster galaxies, observed by Webb, we discover something impossible. To produce that much starlight, these galaxies would have had to convert nearly 100% of all the gas available in their local dark matter halos into stars, instantly and without wasting a single drop. That means no stellar winds blowing gas away, no supernovae disrupting the clouds, and no radiation pressure pushing back. It requires a level of star-forming efficiency that violates nearly every fundamental principle of fluid dynamics and thermodynamics we have ever established in the laboratory. It is the equivalent of buying a fleet of luxury cars on a minimum wage salary. The budget simply does not exist. The second horn of the dilemma is perhaps even more terrifying: the presence of ancient, gargantuan black holes. Deep within the hearts of these impossibly early galaxies, the telescope has uncovered evidence of supermassive black holes. These are not modest, ordinary black holes formed from a single collapsing star. These are gravitational monsters with masses equivalent to hundreds of millions or even billions of our suns. Here is why that completely shatters our understanding of time. In classical astrophysics, a black hole grows by pulling surrounding matter into its gravitational grasp. But as matter spirals into the abyss, it heats up to millions of degrees and emits an incandescent blaze of radiation. That light pushes outward with immense force. If a black hole tries to eat too quickly, its own radiation blows its food away. This fundamental boundary is known as the Eddington limit. Because of this universal speed limit on feeding, a black hole starting from a stellar seed cannot simply gorge itself overnight. It requires hundreds of millions or billions of years of continuous, uninterrupted feeding to swell to the size of a supermassive giant. And yet there they are, sitting at the dawn of time, fully grown before the cosmic clock had barely ticked its first few minutes. Think about the sheer paradox of this scenario. Imagine walking into a vast desert and finding a fully furnished 100-story skyscraper made of solid steel. You check the local supply lines and realize there was not enough raw iron in the entire continent to build it. And you check the construction logs and realize the foundation was poured only 10 minutes ago. Where did the raw material come from? How did the structure rise before the cement could even dry? If these early objects are massive collections of stars, then our laws of star formation and feedback are wrong. If they are supermassive black holes shining with blinding fury, then our laws of black hole growth and cosmic time are broken. We are trapped in a corner where the universe is daring us to rethink our most sacred assumptions about reality itself. Now, take a deep breath, because this is where we leave the comfortable shores of conventional physics and step directly into the truly mind-bending possibilities. When you find an ancient skyscraper standing where only empty sand should be, you have only two choices. Either you admit you do not understand how buildings are made, or you are forced to accept that the history of the ground beneath your feet is radically different from anything you were taught. In physics, when our observations refuse to budge, we have to turn our gaze onto our deepest, most untouchable assumptions. And the most radical idea gaining ground right now is something that should genuinely shake your sense of reality. What if black holes were not born from dead stars at all? What if they were woven directly into the very fabric of the Big Bang itself? Think about how wild that is. For almost a century, we taught every student that black holes are the tombstones of giant stars. A massive star burns through its nuclear fuel, its furnace shuts off, and gravity crushes its core down to an infinitely dense point. But if that is the only way to build a black hole, the James Webb observations remain an absolute, flat-out impossibility. There simply was not enough cosmic time for stars to live, die, and slowly feed up to millions of solar masses. So, what is the alternative? Imagine the universe in its opening fractions of a second. The cosmos is not a smooth, gentle ocean. It is an ultra-dense, seething cauldron of raw energy, fluctuating with unimaginable violence. If those primordial ripples were intense enough, pockets of pure space and matter could have collapsed directly under their own gravity without ever waiting for a star to be born. We call these primordial black holes, or direct collapse seeds. Instead of starting as tiny seeds that had to slowly feed across billions of years, these monsters might have been born gigantic. They were dropped into the cosmic cradle already weighing tens of thousands or even hundreds of thousands of times the mass of our sun. Now, imagine what happens next. These ready-made leviathans did not wait for galaxies to form around them. They acted as colossal gravitational magnets. They sat in the pitch-black darkness of the infant universe, violently dragging in hydrogen and helium from every direction. The black holes did not grow inside galaxies. The galaxies crystallized around the black holes. The cart was not following the horse. The cart was dragging the horse into existence. And it gets even stranger. If you want to push this to its absolute limit, consider the nature of dark energy itself. We know that roughly 70% of the energy in the universe today is this mysterious repulsive pressure that is stretching the fabric of space faster and faster every day. We usually assume dark energy was a quiet, dormant player in the early universe, only waking up and taking over in the modern cosmic era. But what if dark energy was not asleep? What if there was a sudden, violent burst of early dark energy just after the Big Bang, a brief, explosive kick that supercharged cosmic expansion and fundamentally altered how gravity pulled matter together? If that happened, our entire cosmic clock is miscalibrated. The universe might have evolved through its infant stages at a frantic, accelerated tempo, building giant cosmic structures in what would seem to our modern instruments like the blink of an eye. Think about what this does to our understanding of the universe. It means the neat, linear, orderly story we have told ourselves for generations, a slow, patient climb from simple atoms to stars, from stars to dwarf galaxies, and from dwarf galaxies to grand cosmic webs, is an illusion. The early universe was not a quiet nursery. It was an explosive, chaotic pressure cooker where the rules of assembly were running on overdrive, and where the most extreme, terrifying gravitational anomalies were setting the stage before the first light of normal stars could even break through the dark. We are not just tweaking our formulas at the edges. We are being forced to consider that the opening chapters of our universe were governed by mechanisms so alien and so powerful that our current physics is only just beginning to catch up. Let us strip away the comfort of our scientific arrogance and face the hard truth standing directly in front of us. In theoretical physics, there is an unspoken psychological trap that catches even the greatest minds. When our models work brilliantly for decades, when they predict the motion of planets, the bending of starlight, and the faint hum of the Big Bang with exquisite precision, we fall in love with them. We begin to confuse our mathematical maps with the actual wild territory of physical reality. And when reality refuses to match our map, our first instinct is almost never to burn the map. Our instinct is to patch it. We invent invisible knobs to turn, we introduce new adjustable parameters, and we convince ourselves that just one more tweak will fix the entire picture. History has shown us this exact drama before. Centuries ago, when astronomers watched the planets wander across the night sky, their observations began to deviate from the pristine sacred dogma of circular orbits centered around the Earth. Rather than accepting that the Earth was not the center of the universe, they invented epicycles, complex artificial circles within circles. The system worked on paper, but it was a clumsy, very desperate attempt to save a fundamentally flawed worldview. The hard truth we must confront today is that modern cosmology might be standing right at the edge of its own epicycle moment. Look at the full landscape of what we are seeing. The James Webb Space Telescope did not arrive in a vacuum. It entered a cosmological community already quietly trembling from what we call the Hubble tension, a deep, very unresolved discrepancy between how fast the universe is expanding today and how fast our standard model predicts it should be expanding based on the early universe. For years, some hoped that better instruments would make the tension disappear, that it was merely an error in measurement. Instead, Webb confirmed the tension. And now, Webb has piled on this new, glaring crisis of impossibly early massive galaxies. These are not two separate, isolated glitches. They are two violent fractures appearing in the very same pillar of physics. They are telling us that our standard model of cosmology, the triumphant lambda-cold dark matter paradigm that has defined my entire professional career, is showing severe signs of structural fatigue. Consider what is really at stake here. To make our standard model work over the past several decades, we already had to introduce two vast invisible placeholders into our equations. We had to conjure dark matter, a mysterious substance that makes up 85% of all the matter in the universe, yet which no detector on Earth has ever directly touched or identified. And we had to introduce dark energy, an even more enigmatic repulsive pressure that makes up 70% of the total cosmic energy budget, the fundamental nature of which remains a complete enigma. Think about the humility that requires. 95% of everything in the universe is made of components we cannot see, cannot touch, and cannot fundamentally explain. We have built an extraordinary, elegant palace of knowledge, but it rests almost entirely on dark foundations we do not truly understand. And now, when our observations of the infant universe stubbornly refuse to align with the predictions of those very foundations, we have to ask ourselves an agonizing question. Have we just been adding modern epicycles to our equations? Have we been forcing the cosmos to fit into our human desire for simplicity, symmetry, and neat timelines? The hard truth is that the universe is under no obligation to be simple, comfortable, or easy for human brains to decipher. We are conscious primates perched on a tiny rock, drifting through a dark, unfathomable void, trying to reconstruct the opening act of an infinite drama using light that traveled across billions of years to reach our eyes. It is humbling. It is disorienting. But in science, the destruction of a comfortable theory is not a defeat. It is the only way genuine revolutions are born. When our old ideas shatter against hard data, we are finally pushed to discover what lies underneath. We are standing on the very threshold of what might become the next great revolution in human thought. Every time in the history of science that our measurements have clashed with our bedrock theories, the universe was not trying to confuse us. It was inviting us into a deeper, a more breathtaking layer of reality. Think back to the late 19th century. Physicists believed the great edifice of physics was essentially complete, with only a few minor loose threads left to tidy up. But when we pulled on those loose threads, the entire classical world unraveled. Pulling on the constancy of the speed of light gave us Albert Einstein and the mind-bending reality of space-time curvature. Pulling on the strange behavior of glowing black-body radiation gave us quantum mechanics, revealing a microscopic world governed by uncertainty and entanglement. Today, the James Webb Space Telescope has handed us a brand new loose thread. And when we pull on it, we might be unraveling the standard model of cosmology to make room for something far greater. If these early monster galaxies and ancient supermassive black holes refuse to fit into our standard timeline, it means the physics of the early universe held secrets that neither standard general relativity nor our current models of matter can fully account for. It forces us to ask whether gravity itself behaves differently across cosmic distances, or whether the fundamental constants of nature were subtly shifting in the extreme crucible of the early universe. It brings us back to the ultimate dream that has driven my own work for decades, the search for a unified theory, a framework of quantum gravity that seamlessly weaves the laws of the very large with the laws of the very small. In the ferocious, ultra-dense furnace of the first fractions of a second after the Big Bang, quantum physics and gravity were locked in an intimate embrace. If Webb is showing us the cosmic fingerprints of that primordial union, we are witnessing the birth pangs of a new physics. We are living through one of the most exhilarating eras in scientific history. We are not spectators watching a finished play. We are active explorers navigating uncharted territory, mapping a cosmos that refuses